Hello everyone, my name is Chris Fitzpatrick and welcome to my Physics 2212 Lab 4 presentation. The purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. The formulas and rules in this lab were Ohm's law, which is voltage is equal to current times resistance. Capacitance is equal to charge divided by voltage. The node rule, which means that the current in is always equal to the current out. And the loop rule, which means that the total potential difference in a loop is always zero. The experiment 1 instructions and results. Construct a circuit in CCK with two 1.5 volt batteries, one ammeter, one 47 ohm and one 100 ohm resistor, and another ammeter. Predict the resulting current from the circuit for both ammeters. And the current is equal to voltage divided by resistance, which is 2 times 1.5 volts divided by 47 ohms plus 100 ohms, which is equal to 3 volts divided by 147 ohms, which is about 0.0204 amps for both ammeters. These results are reflected in CCK. And when the ammeter is inserted backwards, the ammeter returns negative 0.02 amps. Then replace one of the ammeters with a voltmeter. Describe and explain the new readings on both meters. The voltmeter reads negative 3 volts and the ammeter now reads 0.00 amps. This is because the potential difference is recorded by the voltmeter and the resistance of the voltmeter is very large. Next, remove the voltmeter, close the circuit, and measure the potential difference for each part of the path around the circuit. And I recorded 3 volts around the batteries, negative 0.959 volts around the first 47 ohm resistor, and negative 2.041 volts around the 100 ohm resistor. I recorded the current I, which was 0.02 amps. I then also calculated the potential difference in the circuit, and went from 3 volts, change of 0 volts, negative 0.959 volts from C to D, 0 volts from D to E, negative 2.041 volts from E to F, 0 volts from F to G, and 0 volts from G to H. And that follows the loop rule because it sums up to 0 volts. When you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? The ammeter reading doesn't change when connecting the voltmeter because the resistance of the voltmeter is very large. Now, replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. What happens to the current through the other ammeter? Why? The current through the ammeter increases to 0.06 amps because the path of least resistance is through the ammeter in parallel, which means that no current goes through the 100 ohm resistor. Then I calculated the resistance of the following circuit elements, which can all be seen here. For experiment 2, you'll need a 10 ohm bulb, a 20 ohm bulb, one 9 volt battery, and a 200 millifarad capacitor. Connect the batteries with a 10 ohm bulb and capacitor in the series. Disconnect the battery and connect the capacitor directly to the 10 ohm bulb, then discharge the capacitor. Repeat with the 20 ohm bulb. And what happens is the bulb shines, dims, and eventually turns dark, and the same thing happens when directly connecting to the bulb. The charge and discharge times, which might have human error in them, are approximately 10.5 seconds and 14.2 seconds for the 10 ohm bulb, and 20.4 seconds and 27.5 seconds for the 20 ohm bulb, which makes sense because something with a larger resistance would take longer to charge. Alright, for experiment 3, set up a circuit in the CCK with a 9 volt battery, a 20 millifarad capacitor, and a 30 ohm light bulb. Measure the voltage across the capacitor with the red voltmeter lead on the positive side of the capacitor. Set the capacitor discharging and plot 20 seconds worth of voltage versus time data on a natural log delta V divided by delta V0 versus time plot. Use this plot to calculate RC, and use a stopwatch and to check if the computed value agrees with the RC value of the circuit in the CCK. And here is my data, and here is the graph of the natural log of delta V versus delta V naught versus time. And here's the line of best fit. The slope is equal to negative 1 divided by RC. It's approximately 6 seconds, which means that it does agree with the RC value in the circuit of the CCK. Additional questions. What if you were doing this lab in real life and used a regular actual ammeter instead of an ideal simulated ammeter? The real ammeter does not have negligible resistance, which will lead to less accurate readings. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? And the answer is our ideal model would predict that the capacitor would reach full charge instantly, but due to resistance, this would not happen in real life and the charging would take time. Thank you for watching, and I hope you have a wonderful day.